This week, the key concept is duality. And duality is quite a remarkable feature of linear programming, and it's of interest theoretically, but it's also very important practically. And the basic idea is that problems come in pairs. For every maximization problem, there is an associated minimization problem called its dual. For instance, in economics, for instance, profit maximization will be very close to cost minimization. That's the kind of duality. So you can see straight away that it's something that could have important practical implications. It also has important applications in minimizing the amount of work you have to do when you do linear programming problems, as we'll see later on. Now, the idea is that for every maximization problem, there's a minimization problem, and these are closely linked in the sense that if one problem has a solution, the other one has a solution, and when the solutions do exist, they're equal. So let's see how this works. Let's start off by writing down a problem in a particular form. Suppose we've got a linear programming problem where we're maximizing a linear constraint, a linear condition subject to some linear constraints. Now, previously we always arranged things so that the right-hand side was non-negative, and we could do that by multiplying through by -1 if necessary. But now we're going to rearrange things so that the inequalities are all less than or equal to inequalities, and we're not going to worry about whether the right-hand side is positive or not. So this will be useful for us just from a notational point of view rather than a calculation point of view. So we rearrange our constraints like this, where the b's here are now positive or negative. And the point of this is then we can write the problem in terms of matrices, because this system of inequalities can be written as AX less than or equal to B, where B is the column vector of the resource values and the A is the matrix of coefficients. So we've got C is the row vector of cost coefficients. A is the matrix of constraint coefficients. B is the column vector of resource values. And X, that appears here, is just our vector of decision variables, but written as a column so that we can perform the matrix multiplication A times X. So we've written it in this succinct matrix form so that we can then write down what the dual problem is. The dual problem is a minimization problem. It's a minimization of a new variable which we'll call y, and it's given by B transpose U subject to the condition A transpose U is greater than or equal to C transpose. Remember, the transpose of a matrix is the matrix you get just by reflecting in the diagonal. So in particular, a transpose of a column vector will be a row vector. The transpose of a row vector will be a column vector. The original problem is called the primal problem, and its dual is called the dual problem. So you can see the process you go through is you can write down the system in matrix form, you transpose the matrix, you interchange the roles of B and C, you reverse the constraint. You see now here that the constraint is greater than or equal to, and the problem is minimized. So you change maximize to minimize. Now in practice, while you might want to go through this process explicitly the first couple of times you do it, where you take the problem, write in terms of matrices, and then perform these 4 changes, and then write down your answer in usual form. While you might want to do that once or twice, ultimately we want you to be able to just take a linear programming problem and write down its dual without having to go through the intermediate steps of writing down the matrices. Now the main theorem is this duality theorem, which says that the primal problem has an optimal solution if and only its dual has an optimal solution, and when they exist, they're equal. So that's the famous duality theorem. In practice, what's even more important is this little lemma which gets used in the proof of the duality theorem. So in the notes, you can, printed notes, you can look through the proof. There's an explicit proof that you can go through for the duality theorem. The duality theorem is certainly one of the more important theorems in this course, and this lemma plays a key part. Now what the lemma says is that if you have a primal problem and you compute it by going through calculating the different tableau, then when you look at the final tableau that you have in that process, and you look in the bottom row in the columns of the slack variables, the numbers that appear there are in fact the solution, the coordinates of the dual problem. So when you solve a linear programming problem, you obtain the solution both to the primal problem and to the dual problem. Both of them are there. So let's look at this in practice, because you definitely need to be able to have to use this lemma, and you'll want to use this lemma because it can save you time. So let's look at this problem, and suppose you were given this minimization problem. You notice here that these inequalities are both bad as far as the simplex algorithms are concerned, and you would have to introduce a slack variable for each inequality, and you would have to introduce an artificial variable for each inequality because they're bad inequalities. So you would have to use the two-phase or big M method, and you would have, well, 2 decision variables, 2 slack variables, 2 artificial variables, total of 6 variables. However, if you look at the dual problem to this problem, well, the dual problem to this problem is this one here. And here the inequalities are good. So you don't need any artificial variables. So you don't have to use two-phase or big M. In fact, in this problem here, here is the first tableau. After 2 steps, we get this final tableau. It's very simple. And this gives us the solution for the dual problem, and in the final tableau, in the bottom row, in the columns of the slack variables, here, these numbers here provide the solution to the original problem. So here the solution are half 0. These are the coordinates of the decision variables of our primal problem that provide us with the optimal solution. Moreover, the optimal solution is the solution of both problems, so it's this number 6. So the solution to our original problem is y is 6 at u1 is a half and u2 is 0. And so this process of using the dual can save you a lot of time. And the general idea is you look at a problem, every time you look at a linear programming problem, you need to decide, do you want to solve it, or is it better to solve its dual? And the way you answer that question is simply by asking yourself, well, how many artificial variables are involved? If I look at if one of the problems involves fewer artificial variables, then that's the one you would do.